So just a quick word about lattice energy. So lattice energy, I've seen it defined like this equation. I've also seen it as the reverse. So we've got gaseous ions and they're forming whatever the compound is. Lattice energy applies to ionic compounds. So remember Coulomb's law, remember this, the amount of energy that is released when this bond forms right here, the amount of energy released is going to depend on the value of those charges. +2 and -2 are going to tend to drive that lattice energy up. Also, the smaller these ions are, is going to tend to drive the lattice energy up. So if it's reversed, so we look at this, we know the value of, for this equation should be a negative delta H value. Right? This lattice energy should be very exothermic because this bond that's forming is very, very strong. And so that's something to consider. If you think of this reaction in reverse and imagined taking sodium chloride and turning it into gaseous ions, I think it's pretty easy to imagine. You would need to put in a ton of energy to get that to split apart. So when those things form, a lot of energy must be released. All right, but there's some equations that you could put together, sort of like Hess's law, where we're adding equations together to figure out the energy associated with another equation. If you were going to do this, I would say start with your product there and say, okay, I know that there's this heat of formation value, and you've got your mole of product, and what elements does it come from? Sodium would be solid, and chlorine would be gaseous at 25 degrees Celsius and 1 atmosphere. So this is delta HF, and you have a value for that. After you have this, this is good, right? But you need to get rid of these. So you need to figure out an equation that's going to get rid of solid sodium. And you need to get a gaseous ion, which that should look like ionization energy. So if you need a gaseous ion, you want a gaseous atom of sodium. So we're getting rid of sodium. So we put solid sodium on the product side, get to gaseous. This is deposition. It's the opposite of sublimation. So I just wrote delta H, negative delta H of sublimation. Whatever the energy associated with sublimation is, this is going to be the reverse of it. Next, so that would cancel these out, and now we've got on the reactant side sodium gas. We want a sodium ion, a gaseous sodium ion. So that's just the reverse of ionization energy. We take sodium gas, turn it into a sodium ion and an electron. So you see that's negative I1, that gets rid of that. So now we have another reactant. So we're good with that one. We got to get rid of an electron, and we still got to get rid of half a mole of chlorine gas. So we need to get one chloride ion in the gaseous state. So we're going to need to break that bond, and that would be a mole of chlorine, turn it into a mole of 2 moles of atomic chlorine gas. That's bond energy. I wrote the whole equation and times 1/2, but I kind of like to just put those coefficients in there. So I'm getting rid of the 2, I'm putting a 1/2 here, and I'm putting a 1/2 here. So it'd be negative bond energy, right? Bond energy is talking about breaking this bond, and here we're really talking about forming it, so it's got to be negative. But now I can get rid of chlorine. And now I have chlorine gas, and I want a chloride ion, so this should look like electron affinity. So I'm going to put chlorine gas on the product side, add an electron, and make chloride gas. Now this is the reverse of electron affinity. So negative EA. Get rid of that. The electron, we have an electron on each side. If that doesn't work out, you did something wrong. So we have everything we need for this equation. So if we look up values for these, we just need to reverse those 4, cut that one in half, combine it, and you'll get the lattice energy